Okay, let's see here. Okay, well, I'm shared here, and let's bring this guy up here. Okay, does everybody see this?
Yes, indeed.
Yep.
Okay. Guy, can you see this?
I got it.
Okay, good. All right, so I'm just going to continue on from where we left off on Tuesday. Basically, on Tuesday, we looked at kind of the real fundamental aspects of binary numbers and things like adding and BCD formats, octal, hex, and then how to build a truth table, basic circuits, basic gates, things like this. So we're going to move forward in this. We're still in the combinational logic area. And I think the best way is kind of the way we ended up last time, which is I'm going to go through this these slides, and then I'm going to call up some of the information that I've sent you guys to look at, things like some of the labs and some of the exercises that I work with the students to kind of help them grasp some of these concepts. So today, really looking at the course layouts, we're looking at truth tables, minterms, maxterms, the Boolean laws, and then tackling, the hardest topic in digital electronics, which is Boolean reduction. And this is something that I've actually spent a lot of time trying to figure out how to convey this information to students. We'll talk about a lot of the problems that they face doing this. Something I call the cheat sheet, which is a sort of an algorithm for how to do this that I've developed, which works very well when applied correctly. Some illustrative examples, and then one of the reasons that you actually do this is so that you can do designs with just NOR and NAND gates. And then, of course, we move to K-maps, which is where you jettison the Boolean reduction for the most part, to the great delight of all the students. Most books all present it in one particular way for doing K-maps. It's a way that I don't necessarily agree with because I've seen students consistently make mistakes. So I've got more of a Venn diagram kind of method. It's not exactly Venn diagrams, it's the same concept. And seems to work a little better for students. Then the overall design picture about now that we have all these tools at our disposal, how we can move forward. Okay, so the first thing is basically looking at the truth tables. And some people, when they teach this, and maybe I don't know if it's necessarily critical, but I do like to emphasize the concept of minterms. Basically, that whenever you have a function that is a combination of these minterms, it's helpful to reference them. So basically, if you have a function and this is 4 variable input, you basically say, okay, the function is 1, and you just rattle off the minterms. It's at 2, 3, 14, 15, something like this. And that's helpful for when students are in the lab, when basically we're sitting there looking at the boards and flipping switches, and I say, okay, what are the, if there's a whole bunch of 1s, I'll say, okay, what are the zeros on your truth table? They say, oh, those are 8 and 12. Okay, well, I can dial those straight in. I don't have to sit there and go through the entire chart row by row. So it's helpful for them to grasp that concept. So also, when we start moving over towards K-maps, the K-map cells are referred by their minterms. Okay, so this is something that I've worked with the students quite a bit. Some people don't cover it. I do, and I think it's very helpful. Maxterms, on the other hand, is more of a side topic. I think if you take it, I'll put it this way. Most courses do include it. At least it's talked about peripherally. Well, now, whether or not you actually run exercises and do things with it, maybe not. Maxterms are mostly helpful if you've only got a small number of zeros and a whole bunch of 1s. So then you can frame the solution in that form. And they're focused on the zeros. And it is kind of a good exercise to go back and forth between them because it helps them kind of, do a little bit of Boolean algebra in that regard. So I do like to emphasize the minterms. I think they're very important. Now, the functions, of course, can be written either way. It's your choice. This is an example of function that I have here. So it's either written in sums of minterms or products of maxterms. Most students, by the way, have never seen, they've seen a summation sign, but they've never seen a product sign, a capital pi. That's just something that students have never seen mathematically. I think I'd only seen it once before this class, and it was in some sort of solid-state physics thing. Anyway, so for some given function like we have here, of course, you have the minterms 0, 1, 3, 4, 6. Okay, you see them directly from the chart where the ones are. That's what I try to tell students. This is why it's very helpful. So if I'm in the lab and I'm testing the circuit, okay, where are the ones, where are the zeros? Okay, the ones are there at 0, 1, 3, 4, and 6. I've got zeros at 2, 5, and 7. And of course, you can write the function as a product of those max terms. It's a pretty good way of looking at things. You know, we're actually not going to. I'm not going to talk a lot about doing K-maps with max terms, but I have a tutorial which covers it. Okay, so the students do have a difficult time understanding exactly why these are equal. They look very different. You know, even when you kind of go into De Morgan's equivalent, which we'll talk about a little bit, you're not looking at, you know, you're not actually, they're not really equivalent in this regard. What you're really doing is you're telling them, you know, you're aiming for the zeros on one, you're aiming for the ones on the other. They're inverse functions. So, so you can prove. So if you look at the sum of the minterms, which is this equation 1 here, that's what you have. Or you look at the product of the max terms, which is equation 2. So the question is, are they equal? Well, they should be equal. They better be equal. That's the theory. So to do this, it takes Boolean algebra, which we're going to cover. We'll come back to this specific example. So I like to tell them that, okay, it's you know, even though we sit there and I try to emphasize in the class that this is A prime, B prime, C prime, or A prime, B prime, C, you know, you still use the nomenclature of regular algebra, so this is the sum of products form. Okay, so it actually looks like a sum of products terms, and the other one, of course, is the product of sums. Okay, so SOP and POS. And that's somewhat important because one of the things that we state in class is that students really need to be comfortable with this SOP form. So basically to do any kind of Boolean reduction, Boolean algebra, what you really need to do is you really need to make sure that everything is spread out in that SOP form. I try to emphasize that to the students. Okay, so, all right, Boolean algebra. And these are just my notes. I write these things down kind of at the beginning of the section. But you know, by far, this is the most difficult topic in digital electronics. I said last time that it has a lot to do with math maturity and what students can do and what they can't in their level of experience. You know, one of my approaches to this is to raise the math level, the requirement for the course, and that's helped. But what they have a very difficult time grasping Boolean algebra concepts and applying theorems. Seems to be something that's very difficult. It's on the level of doing math proofs, you know, to some extent. And just like doing math proofs, you know, you don't really get proficiency until you've done a whole bunch of them. And students, you know, probably can't really convince them to go and work out, you know, hundreds of Boolean algebra problems. But I do give them a lot of solved problems and tutorials and things. Number 3 was something that I found, which is actually fairly shocking, and that is that many students have difficulty with one particular basic algebra notion, which is factoring out the A out of AB plus A, basically. I have so many students that cannot do this, and I don't know why. I see it every term. I have seen it for years, that students, if I say, okay, A, B, or A, factor out the A, what do you have left? Half the students will say B. They won't have the 1 in there. And I'm not exactly sure what that is. There's some sort of a lack of understanding at the basic level there. However, if you tell them to do, you know, FOIL, for instance, they'll just write it right out because it's just something you've memorized. But this one, the concept of doing distributive property many times eludes them. And I've seen it at 4-year school. I've seen it at 2-year school. It's just there. And I don't know why I see this. I don't know how to approach it. And also, to some extent, you know, there's only so much I can help them with their basic algebra because that's assumed. Yeah. Since the next step in the DIG course is to cover K-maps, it does beg the question of why even do this. why go through Boolean Algebra? Why go through Boolean Reduction? There's software that does this for designers. People are not sitting around, at Intel doing Boolean Reduction. So why is it? One easy answer is required for the CTAG tag approval. It's actually one of the outcomes. Okay, so to some extent, it's there until someone changes. A more encouraging type of comment is that it emphasizes a lot of fundamental aspects about how binary signals interact. Basically, if you understand the concept of two things in an AND gate or an OR gate, you understand that things can be simplified down, kind of gives you respect for what's going on inside the circuits. The last one is, it really is the most effective tool for understanding this, is that if you combine it with an appropriate lab, it really drives home the importance of reducing the complexity of a function. So I'll show later that we have a lab where I make them wire up this long circuit, this long function, and then they do the Boolean reduction, and then you find out it's like A, B, or C, or something like that. It's like 2 gates. You're like, oh, yeah, that's a lot easier. Well, yeah, that's right. So there's your motivating factor, because who wants a rat's nest of wires and 5 chips when you can do it with 2? And so I try to tell them that that's the reason that you do this, and that's also the way it works in the real world. Real engineers designing these types of microprocessors and down to the gate level and everything like this, they're trying to pack as much as they can on the real estate that they have. So yeah, optimization of logic design is critical. Okay. So one of the things I like to do when I'm teaching this class is I tell them, okay, what aspect of this stuff really looks like normal algebra? Okay, so what is the stuff that it doesn't take really that much of a stretch for them to understand versus what is really bizarre, okay, and really just indigenous to Boolean algebra. So the commutative laws are pretty straightforward. Just it doesn't matter which order these things are multiplied in. It doesn't matter which pins that you stick into the gates in which order. Okay, most students don't have a problem with that. Associative laws are pretty much the same as well. Basically, if you want to do A, B, or C, and you don't have a 3-input AND gate, you can use two input AND gates. That's actually, we do that in a lab. They actually have to hook that up and show that. Same thing for the OR. We actually do have a 3-input OR, and then we also show them that they do the 2-input OR. And it doesn't matter which order you put all those things in. Usually, since the 3-input gates are not standard, I always tell them that for most problems to do everything in 2-input gates, which gets some tricky when you start dealing with NANDS and ORs and stuff. But this is not too bad. And then distributive laws here, which is actually the ones where I've been surprisingly having problems. They do have some difficulty with that. Of course, the second part there is just FOIL, which they have no problem. But the first part, they sometimes just can't factor out. And I even had a comment from one student who looked at it, and after 10 minutes, he just said, well, I guess I'm just not going to learn that, which stunned me. I don't know how to respond. But anyway, so those are not too bad. What differs, okay, then you start getting into, what is a little bit odd. Stuff like, x or 0 equals x, that actually looks like normal algebra. X or 1 equals 1, of course, looks nothing like normal algebra. And I try to tell them, they spend a lot of time trying to memorize a lot of mathematical functions. And I tell them, I don't want you to memorize these. I just want you to look at them and understand them and think about what's going on. X or 1 is 2 signals going into an OR gate. It's the variable x and 5 volts, which is 1. An OR gate is going to be 1 if any input is 1. Therefore, since one of them is definitely 1, it's 1. It doesn't depend on x. So I try to rationalize these things with them to make them understand what exactly these come from, because I don't want to just put up a bunch of stuff that just memorize. X and 0 is 0. Well, that's because you put 0 into an AND gate. Both inputs have to be 1 for the output to be 1. Therefore, that has to be 0. X and 1 is just x. That looks like regular algebra, but here it's a little bit different because we're talking about an AND gate. As long as 1's 1, it just depends on what you're putting in. So that kind of stuff is really trying to get them the idea about how this works. Some of them look odd, and really just I don't want them to just sit there and memorize it. I want them to understand. X or x equals x. That's definitely not normal algebra. And basically, you can show that on a truth table, or just think about it. I mean, if you XOR, you got two same signal going into an OR gate, it's either 0, 0 or 1, 1. You know, if they're both 0, if the answer is 0, and if both 1, it's 1, therefore that's what you have. Same thing with X and X. If they're both 0, it's 0, if they're both 1, it's 1. So that kind of thing. When you know, involution law there, that's just nothing more than just take the complement twice, you get back what you had. And that's just like two negatives in algebra. Most students don't have a problem with that. X or X prime equals 1. That's an interesting one. I try to tell them, if you've got a signal, I said, keep in mind, this thing's binary. You know, if X is 1, X prime is 0, vice versa. So that means that one of those has to be 1, you know, going into an OR gate. Therefore, that answer has to be 1. The same thing with what's going into an AND gate. One of those has to be 0 if it's X and X prime. Therefore, that necessarily, the output has to be 0. So I truly try to emphasize them to kind of get away from math and think about it in terms of gates as much as possible. And then you just kind of get comfortable with the algebra itself and kind of move through it. Which brings to what I call the Boolean distributive law. That's what's called in the books. I call it the second most important law. And this is one that the students have to work out. And it's this kind of unusual distributive law. X or Y z is equal to X or Y and X or Z. Doesn't look anything like normal algebra, and certainly wouldn't hold except for in some unusual situations. So what I do is I'll prove this in class. It's just a few steps. It's not very difficult proof to make. And then I'll actually ask them to do that on a quiz. But usually I'll ask them to do it. I'll say either do it by Boolean algebra or you can show it just truth tables. You know, just do the truth table for all these functions and show that this is true. You know, I just want them to understand that this is true. And the thing about it is, it comes up a lot. It comes up an awful lot in Boolean algebra. And what I say is that the most usual situation where it's helpful is in this situation where it's like A or A prime B, where X and Y are complements of each other, and then it helps you, A or A prime, so that's 1, therefore it just comes down to A or B. This kind of a situation is very, very common, and one that students need to learn. And it's lots of exercises, lots of quizzes and stuff given on it to have them understand what's going on. Also, I try to emphasize the fact that if you really look at what's going on at A or A prime B, if you look at the number of gates that are involved with that, well, you've got an inverter, you've got an AND gate, you've got an OR gate. That's 3 gates. Those are 3 different gates. That also makes it 3 chips. Okay, so that's 3 chips that you've got to put power and ground to and wire up. Your answer is A or B. Well, there's no inverters. That's 1 chip. So you've actually just by doing this one step, you've reduced 2 chips out of 3. And just by doing this one. So just a little motivation like that, actually, to get them to understand, because they learn pretty quickly when they start wiring things up that, you know, that it takes a while and it's very easy to make a lot of mistakes wiring circuits. Okay. Then comes the most important law, De Morgan's theorem. This is critically important, and the students have a little bit of difficulty with this. Takes some time for them to work on that. Basically, I said there is a direct algorithm for doing this. Okay, so you change all the variables to their complements, change all the ands to ors, change all the ors to ands, and then take the complement of the entire expression. They usually forget the last part. Okay, because they get excited about it. So basically, AB, if you go through that, change each of the variables. So it's A prime, B prime. You change the and to the OR gate, and then you invert the whole thing. So it's A prime or B prime. The most useful situation is the third one of those, which is in that particular NOR, A or B prime goes to A prime, B prime. So that having that, I just do a lot of exercises with them, trying to work through and understand exactly what these are. The graphical representation sometimes helps for some students when they can't do it. I say, okay, if you look at something like AB and it's an NAND gate, of course I just put an AND and an inverter there, but that's an AND. And then basically I say, okay, well, if you invert each input and then you change the gate and then you invert the output, you get what's over on the right side. So then you get, you know, A is inverted going in, B is inverted. It's now an OR gate, an AND gate, and the inverter is invert it again so it's not there. So this is sometimes helpful because the students can kind of see exactly, kind of physically what's going on. And this is another way to approach it, which is always a good idea when you're teaching students, if you can, is try to present things in a couple different ways, because you never know what's going to click for students. Sometimes it's someone else explaining it to them than you. So if we go back to the original problem that we had, this was the SOP versus the POS problem. And this is a lot of stuff to look at. I agree with that. You know, I don't think it doesn't, Boolean algebra doesn't make great reading. But basically, if you look at it and you're applying those laws, you know, what do you have? Well, you have, first thing you have to do is you have to I tell them, okay, you have the right side, which is this product of sums. I got to multiply all that stuff out, you know, and make it into SOP form. So that's what you do. And so then I tell them, you know, you really need to look at like A prime, you know, that's going to be 0. B prime is going to be 0, things like this. So you spread them all out, and then you got to group things up. The problem is, and this all works out fine, they come out to be the same, but, you know, I did this. You know, this wasn't a student. Okay. So the question is, you know, how does a student know how to do this? Okay. We'll get to that just a second. Okay, just a second. Okay, so what this does, as far as the Boolean algebra, we haven't really talked about Boolean reduction too much, but which is the motivating factor is to be able to do things like this. So the first part, as far as the rubric is concerned, is for the CTAG stuff, is did you cover all these materials? You know, talk about things like the basic laws of Boolean algebra, which is all those basic laws. You know, the SOP and POS algebra. You know, can you do that kind of stuff from truth tables? Can you relate the Boolean operations to appropriate logic gates? You know, which is actually quite critical. You know, that's this one right here. And that's pretty critical because I do want them, like I said, I really try to emphasize the fact that this is not just completely abstract algebra. This is related to actual signals and gates. So it's not as far as where I think most courses fall. Most courses can easily fall in this the very highly applied skills area. I don't think that's really too difficult to achieve, and it usually works out. Okay. Any questions right now at this point? All okay?
Yeah, I'm fine with this.
Okay. All right.
I see the same problems that you see with most of my students too.
I'm sure you do. Yeah. I think that's why when they switch to K-maps, they're just so happy.
I don't think happy is the right word. Ecstatic would be better.
Yeah, well, relieved, I'm sure. And also a sense of why did we go through all that? Because it looks like hazing. But
well, I tell them not to ask me that when I first introduce K-maps. Don't even ask me why they didn't see this first.
Yeah. Well, that's and there's some validity to that, but like I said, I think there is some benefit to it because I think you need to work with this and really try to get a feel for it. So I do think there's some benefit to doing that. Okay. So like I was saying, one of the things that you have is trying to get the students to understand a method for doing this. The books all present roughly the same stuff. They present your logic expressions. You know, they present all of the laws, all the rules. You know, but they don't tell you, and they'll give you some examples about the laws and the rules, but they don't really tell you how to go about solving these problems. So it's like here's an example, for instance. You know, students aren't aware, for instance, that you know, if you start combining terms, you can use one term to be combined with two different terms. You know, this guy in the middle can be used twice. Well, why can that guy be used twice? Because you could duplicate it. There's an A or A equals A rule in Boolean algebra, and you can duplicate it as many times as you want. So I show them. I try to give them a little bit of methodology. It's like, okay, well, you know, there's a lot of bookkeeping and this kind of stuff. You know, and I think that's not the worst. That's not the worst thing to have. A little bit of keeping track of stuff so it doesn't get lost. let's say if you're going to be combining these terms, you want to be very, very, very clear about it. Here's 1, here's 2, and write down what they are. As you combine this, this becomes very the second most important law, as I call it. It spreads out, and here we have this. Exact same situation for these two. Becomes another second most important law. Here, get this. Then like you write them back out, make some more simple combinations, and then the whole thing goes down to y. That's amazing. So I go from needing two inverters, that's at least, what's 1, 2, that's 2 AND gates, another AND gate, another AND gate, a bunch of OR gates, to something that doesn't even have any gates. It's just a straight wire. So this is an excellent example of how drastically you can reduce functions by doing appropriate Boolean reduction. So the key was, and I didn't develop this for the first several years I taught the course. I just kind of went along with it. But basically, I wanted to really figure out how to do this. So, like I said, it's very much like trying to get students to do mathematical proofs. Unless you do tons of them, you just don't quite get it. And the textbooks don't do a very good job of solving it. So I created a guideline for the students, which works pretty well, and then this is it. So this is kind of the cheat sheet. And basically, most Boolean reduction problems follow this kind of algorithm. So there's a little bit of going back and forth. First thing is you have to convert everything with De Morgan's needed. The problem is that if you have something like this NOR gate that you have here, if it's got a term outside it, you can't bring it through until this thing is converted. Students will try to do it. They'll try to bring a C in here or D or whatever it is and expand it out, but it won't work. So the first thing they have to do is they have to expand these things out. These NORs and these NANDs, they got to expand them out. That's first thing, because once you do that, then you can write everything out in terms of SOP form. And that's what you have here. So you expand all the terms out. You don't want anything in parentheses. Then you simplify what I call the simple terms. Anything that's like A and A prime, that term goes to 0. Anything that's CC prime that's just the same term. Anything like A or AB is going to be A, because that's just going to be 1 or B, or 1 or X is just 1. All these kind of small, simple, X and 0, stuff like this. Any of those small little things that you see that you can throw terms out, you just throw them out. Then you got to start grouping things and reducing them. I've got this AB. You got to look for common terms. Like this kind of stuff. Get rid of the C or 1 part. Then once you do that, you've probably simplified all the kind of easy stuff down. Then you got to look for terms with this second law, and they're all over the place, and they're frequently hidden, like here. Factor out the C, and then you've got the second law term, and then you bring it out, and there you are. Now, the way this usually works, I probably will revise it at some point, is when you come back up here, then you're coming back up to this and kind of doing this. You're kind of doing a loop like this. And you should be, after going through that, you should be done. There is a possibility that you'll get something that seems like it should reduce, but it won't. And sometimes you can consider adding a 1, adding a C or C prime in there and expanding it out. Most students don't want to, they work hard to get it to the smallest number. They don't want to expand it back out, but sometimes if it kills off other terms, then it's important. That's not done too often. It's done a few times here and there. So this sheet has actually been very helpful. I handed it out to all the students. I put it up online. And kind of following this has been very helpful. So if you look into an actual example, and I like to do this kind of stuff with the students. Okay, let's look at what I'm doing. So I've got this expression here for F. It's got a couple of DANs in there. So the first thing is I got to get rid of those because I can't take the term and bring them all out. So I convert with De Morgan's, and I expand everything out so that now everything is in nice, simple terms. And then I still have some stuff inside this very large parentheses here. Simplify some of this simple stuff, and then expand the stuff out. So all the stuff simplifies, and I just end up with this. Then look for anything with this second law. Okay, well I definitely have that. I factor out a D. I've got the second law here, and then I bring this down here. And then finally I can do a little bit more reduction, group terms and reduce, and then finally I'm down to here, and that's as far as I can go. So most things follow this. Not everything follows this exactly. A lot of times, you don't even need to do De Morgan's. You just go without. But I found this to be pretty helpful, and I certainly hope that if it's something that's useful for anybody else, I think that would be fine. I'd like to see it in the book someday, but I don't want to write a book. So we'll see how it goes. Final comments about the Boolean reduction here is that, like anything else, the students really need to work lots of problems. There's a lot of technique that's involved in developed over seeing problems. You just start seeing something. One thing that you see, I tell students, like if you ever see a literal or a variable by itself, any other thing that has that in it, you can just strike, because if you factor it out, it's going to be one or all these other things. So all that just goes to one. So there is noticing trends and patterns and getting quicker and stuff like this, but you do have to work a lot of problems, and there's only so many that they can do. The students definitely need to be solid in their regular algebra. This is just a there we go. This is a big deal, and I sometimes don't know exactly what to do. You try sometimes putting numbers in there, trying to have them give a bunch of examples. One thing that I did when I had a class, I think I mentioned this last time, I had an advanced class where I gave them a math quiz. I may start doing that. I think there's something to that. Here's some basic algebra problems that I want you to work. I need to see where your level is. Maybe I'll give them some sort of a tutorial or some sort of work to get up to speed. There's a great deal of frustration for the students because they really have no way of knowing if their final answer is the most reduced. They get this because one thing, they may have made a mistake somewhere. Well, one of the biggest mistakes is copying stuff down incorrectly. All of a sudden there's a prime where there wasn't before. They dropped a prime, and that just one prime and it's just gone. It's like I said, there's a lot of bookkeeping. So when they get this answer, they don't really know if it's the most reduced. They're just like, I guess that's it, and they circle it, and that's done. That's tough. I find that without the cheat sheet, I don't let them have them for the quizzes and exams, but typically the students will just look at it and say they don't know where to start. I'm like, okay, well, look at the sheet, try to follow this algorithm. That helps. There are a couple of very common errors that are made. Many students will take A prime, B prime, or AB and make this 1. This happens a lot. Okay, they'll see those two terms and like, oh, those are inverses of each other, and they'll say, no, they're not inverses of each other. That's an XNOR gate, actually. And likewise, the one B there, B is the same thing. They look at these, say, oh, these guys are opposite, therefore, one of them has to be 1. No, this is actually an XOR gate. And then this one, I give lots of problems to students. I do it on truth tables, the Boolean Algebra, the De Morgans, and I still have students that do this, which is incorrect. This still happens, and they'll look at the outside and they'll just distribute the prime right through to everything inside it, and that's just, I try to tell them not to do it, but I still do. So these are kind of these are the real problems with Boolean reduction. It is the hardest part of the class. Now, on one hand, when they make it through it, I get to tell them, hey, this is the hardest part of the class. So just if you're getting this, even on some level, even if you're only understanding the 60-70%, okay, that's fine. We move on. A big part of this is, like I said, conversion of gates to NANDs. This, like I said, I always try to instill some real-life engineering into the digital course, and basically, circuit designers lay out things in NANDs because once they have an optimized layout for a NAND gate, sometimes it's easier to just do things in NANDs rather than going through using a bunch of different types of gates or different footprints. And so I tell them that basically the NAND is unique in that if you try this thing. In that if you look at this, I tell the students, I was like, if you have the same input if you just tie the inputs together, what does it look like? Well, it looks, if they're both 0, it turns into 1. If they're both 1s, it becomes 0. So a NAND gate with the input tied together looks like an inverter. I say, well, that's amazing. Okay, so then if I take a NAND gate and I just put it in, I just use an inverter, that makes an AND gate. Okay, well, that's simple enough. So an AND can be used to make an AND. Then if I take an AND gate and I just look at the De Morgan equivalent, okay, if I invert A, invert B, and I invert the whole thing, that's the same thing as an OR. Well, that's amazing. So once you've got those things kind of nail down, you realize, okay, now I can use the NAND for everything. Because beyond that, everything else is just some combination of those gates, an AND, an OR, or an inverter. Right? Well, the same. Oh, okay, I didn't realize I had that. Okay, that looks better. Okay, so every logic component can be made from NAND gates. Well, that's pretty helpful. All right. So the key to doing this. So the key to doing this conversion is that when you want to convert everything to NANDs, you want to get rid of all those plus or those OR terms. So I tell them, basically you look at something like A, B, or C. This is not something, you don't want to change the A, B part because that's already an AND. You can do an AND with NANDs very easily. So what you do, if you really want to do this with nothing but NAND gates, basically you do this De Morgan. This looks like just X or Y. So the equivalent is X prime, Y prime, all prime. Therefore, you can rewrite the expression like this, AB prime, C prime prime. And that's just 3 NAND gates. Okay? So you can do it all with NANDs, using the NAND as an inverter and as a NAND. So I tell them, basically we go through some expressions of how to do this. On multisim, which is, of course, the software they use for doing circuit layout, one of the options that they have is when they write out, they do something called the logic converter. And they call it up, and it's a nice function. I don't show them until later on because it kind of solves a lot of problems. It'll even do Boolean reduction for them. So I kind of don't show it to them until they've, sweat a little bit. But it goes through, and they one of the options is convert the entire circuit to NAND gates. And so I'll show you one of the labs that we have where they go through and they have to derive it all in NAND gates, and then they kind of hit the button and it just redraws it. And it's an amazing tool, very handy. Okay, so the same situation for NORs. It's not as common in general as NANDs. I'd say NAND, it depends what logic you're using, but it does actually exist. And so the same situation here, the NOR has the same thing. So if both inputs are tied together, it's going to be an inverter. Okay, well that's amazing. That's very helpful. Therefore, you just want to make an OR gate. All you got to do is take a NOR and just put it on the inverter and have your OR gate. That's very straightforward, very simple. Then if you want to make an AND, you're going to go back and do this through De Morgan's again. So you're just going to be looking at the De Morgan equivalent, and that's just going through. So AB is A prime or B prime all prime. So you invert A, invert B, put it all through a NOR, and you've got an AND gate. So you got the same situation. So every logic component can be made from NOR gates. Converting it to NORs, basically here is also again with De Morgan. Except here, instead of getting rid of all those pluses, you want to get rid of all the multiplication terms or all the AND terms. So you don't want to change the plus C in this A, B, or C. This is already, it's just an OR, which is an OR plus inverter, which you can make. You need to expand the AB so that it looks more OR-like. And so that's what you have here. So it's A prime or B prime prime or C. Therefore, this is going to require 5 NOR gates. And the students are a little bit confused because when it's happening, you've got one for the invert for A, one for the invert for B. You got a NOR gate going in. Then you've got an OR, and the OR is going to be another NOR and then another inverter. So it's actually 5 gates. And students sometimes have a hard time realizing that when you write everything out in SOP form, it's this or this or this or this. It's a bunch of OR connections. So at the end, you're going to be doing everything with NOR gates. So you got to be sure to invert. But so a typical type of problem that I give is I'll give them some function. I want them to do Boolean reduction. I want them to put it on the truth table, to write out what it is, and then I want them to, maybe draw the reduced circuit, then convert it to either NORs or NANDs, whichever one that they usually give them a choice. Okay, any questions on this part? Any experiences dealing with these types of stuff? Is this stuff just okay? hearing you much.
My problems, my kids really handle the transition to NANDS and NORs pretty smoothly.
Good.
So I haven't had many problems with that at all.
Oh, that's good. All right. So they usually, you find that they don't have too much of a problem with the De Morgans?
No. They do have problems reducing the Booleans, and I don't give them a cheat sheet like you do, but I think I'm going to try that this year because we're about ready to get into that.
Right.
And but I've never seen them experience any big problems, just the conversions after getting past that to NANDS and NORs.
Okay. Yeah, that's good. That's good. Yeah, I mean, because what I think of in general is that the Boolean reduction is problematic simply because the students just don't know where to start. You know, and they, I mean, you know how it is. You can have all these terms laid out, and if you combine them in the wrong way, you just get stuck. I mean, you didn't even necessarily do something wrong. You just went into a dead end, and that was it.
Yeah. So a lot of them stop for me because they think they have to do one thing first.
Right.
And I try to explain to them, if you simplify one step at a time, you're still going to end up at the same place.
Right.
If you do the steps out of order from someone else, there's not one solution, but I think they feel more comfortable with checklists.
Yeah. Well, give it a try. See if it helps. Okay. Hey, Rob, I saw your name pop up. Are you there?
I'm sorry, did you ask me something?
I saw your name popped up, so I was just checking to see if you were there.
Yes, I am here. Yes.
Okay, great. Okay, good. All right.
Thanks, Ralph.
Yeah, sure. Okay, so now we're going to look at K-maps. K-maps are always, really the saving grace for all this, as we said, for a number of reasons. One, the Boolean reduction, if you do it correctly, it works fine. You know, it's laborious, no doubt about it. But because it's fairly difficult and it's potentially inaccurate, and students do it correctly, K-maps work very well. So usually for this class, I don't look at maps greater than 4 variables. There's, some professors like to teach 5 variables, even 6 variables. They like to do that, and it just gets all kind of Rubik's Cube-like. And to some extent, you have to say that there's software for doing this, and it's or numerical algorithms like the Klein-McCluskey methods and stuff like this. I mean, so I say if you're getting a lot of variables in there, then you just let the computers handle it. But three or four variables, I mean, that's absolutely something the student should understand and be able to do fairly readily. And I have to remind them that that it's not an automatic thing. I mean, there's still a lot of it's a bookkeeping they have to do. They have to. So there's basically 3 steps for doing this successfully. They have to understand and not just memorize how the map is organized and transfer the data from the truth table to the map. So, and the first thing, I mean, there are many ways to snag defeat from the jaws of victory in this. One is by not filling out the map correct. Okay, then you must correctly reduce the map. Reduce it down and choose the proper groupings that you get the optimum answer, and then you have to read the reduced map correctly. So, first thing that I work with students pretty hard on is really understanding how the maps are organized. Okay, so if you look at 3-variable truth table, start with the concept of adjacency. Okay, so basically that when you have something like M2 and M6, M2 is A prime, B, C prime, M6 is A, B, C prime. Thus, they only differ by A. Okay, and so you can see all kinds of this throughout the truth table. You can see things that vary. Look at 1 and 5. Or you look at 3 and 7. I mean, they all vary just by one input. So these things, there's some sort of an inherent symmetry in there, and that's how this map was developed. I don't know much about the person, Karnaugh, who did this, but it actually is next to the Smith chart, it might be one of the more real brilliant things that ever came out for electrical engineering. So I say, okay, here's the map is organized 0, 1, 3, 2, 4, 5, 7, 6. And I say the reason it's oriented in this way is that for every cell that you have, the ones that are right next to it and not diagonal from it only vary by one variable. So for instance, you look at M3, it's got 1, 2, and 7 right next to it. Well, that's because it differs in A, B, and C. There's three neighbors. All right. I also tell them to be sure that, this is not like a flat two-dimensional thing. It, it wraps around so that 2 and 6 are actually connected to 0 and 4, kind of like wrapping around a soup can. Right. So, and I tell them, you have to, you should really take a look at those and see how this is organized. And this is, you need to really remember this, the way it's laid out. Okay. So basically here, I said, so if we're doing Boolean algebra, so there's a couple ways to do this. I haven't figured out exactly the methodology for introducing this. So one of them, I tell them, here's how it's laid out, and I just kind of show them the idea about what we're going to start grouping before we even start reading what we're doing, just to kind of have it. So, so I say that we're doing the Boolean algebra. If you have M2 or M6, immediately you put those in ones in those slots. I don't want them to put zeros in all the other slots because it just makes it look junked up. So just leave everything else blank. Then start grouping all the cells together in powers of 2. And then, like I tell them, okay, it's kind of a theme in this course, is that powers of 2, right? 1, 2, 4, 8, 16, etc. Don't circle things in 5 or 6 or some crazy number, because you can't find expressions for that. And the reason you can't find expressions for that is because this is based on the Boolean system. Okay. So we'd have a map that looks like this. And I say, okay, so what we're going to do is we're going to do the groupings. And then I tried it, and so one of the things about it is, actually the students really like doing the K-map groupings because it's kind of like a game to some extent, which is great. It works out fine. But I said there are some ground rules that you have for the game, which is that you want to group it to the largest power of 2 that you can. You can include any cell that's already been grouped as long as there are new ones in the group and the sides of the K-maps are connected. So I tell them, okay, there's your grouping right there. Okay, and it's because only 2, so you group them together. That's fine, no problem. So I said, okay, let's look at another situation I have, which is this map. And I haven't actually laid anything out. We're not reading the map. We're not doing any reducing. I'm just trying to give them the idea of grouping things together in some sort of logical fashion, the largest binary numbers. I said, okay, so I have another function. These are the cells that I have. So you should be able to group. So there's 1. Okay, so that's a large grouping. That's 4. So one thing I'll have students who'll now go through and they'll say, okay, I've got that 1 by itself. They'll just circle him by himself. I'm like, wait, no. You need the largest grouping you can find. That's those 2. Okay, so you want those 2. They're like, oh, okay, because you can, as long as you have a new one in the new grouping, it doesn't matter. You can keep including other ones that have already been grouped. It's not a problem. So they forget that they can do these overlap groupings, and sometimes they'll forget to do powers of 2. To some extent, if they group in things like 3 or something like this, they see very quickly they can't write down the answer anyway, because it just doesn't make any sense, and they have problems where they can't figure out what's going on. All right, so this is basically the major steps, and the major steps being getting the function onto the truth table, and then getting the proper groupings, circling all the right, getting all the right, everything covered. So now we need to read it, so we got to look at the truth table. Now this is where I venture a little bit differently from books, okay? And my impression about reading, or my opinion here about reading truth tables, about reading the K-maps, is that there's no system that I think is really any better than anything else. I base this way of doing it on, somehow this was taught to me somewhere and I don't remember, but I do see that students mess this up less than what they do in books. Okay, the books are almost always, and I'll bring up the book method in a minute, but this seems to have a lot more success, and it's a little bit more visual. Now, so there are some who are very visual learners. I bring up the concept of Venn diagrams. Have you ever seen a Venn diagram? Well, a lot of them have. You have 2 circles. If they intersect, then that's what's in between. Like, well, that's the concept for K-maps. You just got to figure out where everything is. So I tell them, what you really have to do is you have to understand the truth table and how it's laid out. So if you note that A is 1 for numbers 4 through 7, for those minterms, so if you actually write down those minterms, all 4, for 4 through 7, all of them have A, in their representations. But the 0 through 3 have A prime. Okay, so basically, we represent the top row as A prime. Okay, and the bottom row, okay, is A. Okay, so that's fine, because that says that all those minterms on the top row use A prime, all those on the bottom row use A. Okay, that's fine. So then I say, okay, same thing for B. If you look at B, B is 1 for 2, 3, 6, and 7. Okay, so write those minterms out, they're going to have B. And for 1, 2, 4, and 5, we're going to have B prime. Okay, so then we can easily see that that's B, and those 4 are B prime. And there's 4 each because that's the symmetry of the truth table. That has to be the case. Finally, I say if you look at C, and I want them to think there's nothing special. This could be X, Y, Z, or PDQ, or whatever. I say, but C is your least significant bit. Okay, and I say one thing you want to realize is that C, C is basically splits into even and odd numbers. Okay, so it's 1 for all the odd numbers, even for all the, that's 0 for all the even numbers. So you can pick those out. Such this is C, and those 4 are C prime. Keeping in mind that those 2 are connected. And 0, 4, 2, and 6 are all connected. So this is all basically how the map is organized. Okay, so once they kind of understand why this is the case, then it helps to actually start looking at being able to read it. Okay, so now we'll go back to the example that we just had. Okay, you say, so the key is to look at these regions where the ones, you want to see where the ones are contained. So I really kind of tell them this is the deal. So if you look at those 4 ones that we have that are circled in red, notice that those 4 ones are all contained in B prime. Notice that half of them are in A prime, half of them are in A, and half of them are in C prime, half of them are in C. So basically, you only want to write down those that they're completely contained. So those 4 are B prime. Okay. Likewise, the 2 on top, they're fully contained in C, and they're fully contained in A prime. That should be C, not C prime. So that's an error. Right? Lost my pointer. Not sure what this is. Okay. So anyway, so that's an error there, C prime. So it's actually A prime C, not A prime C prime. So the function is B prime or A prime C. Okay. So they start to kind of get the idea, and then I'd say, okay, well, this is the way it works. If I have just one cell, I just circle one cell by itself, that for a 3-variable map, that's going to leave all 3 of those literals or those variables. So something like A prime BC would be cell number 3, 0, 1, 1. If you group 2 of them together, what you're doing is you're doing Boolean reduction. You're doing like A, B, C prime, A, B, C. So this is A, B, C, or C prime. It goes away and just left with A, B. So you'll get rid of 1. You'll left with 2 literals. Okay. If you group 4 of them together, work out the Boolean algebra, you'll leave yourself with just 1. So that's how when you start circling them, you know what you're looking at. So I knew when I circled 4 of them, that's going to be 1 term. Circle 2 of them, you're going to have 2 literals. If you group all of them, then it's just going to be everything's 1. Okay, so that's why I try to emphasize the fact that if you do the larger groupings, the more terms that you're actually removing, the less wires you're going to have to use, the less gates you're going to have to use, everything like that. And it works pretty well. They really start to kind of get the idea. So here's one more example here, and I say that you really need to keep in mind also that these cells wrap around. Okay, so the first grouping requires this. So we have a grouping here, those 4 that wrap around. Okay, so those are completely C prime. Just going back to the previous slide that says if I group 4 of them together, then I only have one literal. Then the others, and again, you don't want the students to circle just 1. You have a couple other groupings here. I've got this one here, which is A prime, B prime, and I got this one here, which is AB. Okay, so there we are. And so then we have the full function right down below. So I think I start them with on 3 variable maps like this. Some books will do two variable maps, which are these little 2x2 maps. I think that you just get that straight from a truth table. I don't think that's actually it's very helpful. I think three variable, four variable is really everything that's needed. Now, this is what most textbooks do, okay? Just or some combination, some orientation of this. Basically, they'll have this kind of split line that goes up. They'll have BC 0, 0, 0, 1, 1, 1, and 1, 0, and then they'll do A, 0, and 1. So basically 5, if you look right across, 5 is 1, 0, 1, 7 is 1, 1, 1, 1, 1, 0. Yeah, it makes sense. It's perfectly fine. And sometimes I've seen this map done vertically. I've seen the top and the bottom flipped, BC's over on one side, A's on the other. So there's lots of different ways you can do it. And I tell them, I say, you can do whatever you want. That's, as long as you're consistent. As long as you always do it that way, it's perfectly fine. You don't have to do the way that I do it. It makes sense to me. It makes sense to a lot of other students. But I do see them mess this up quite a bit. They get the numbers confused. They won't they'll put like A, B on one side and C on the other, and they won't quite. They just kind of. I've seen them mess this up many times. So I don't proselytize one over the other, but I'd like to present a different alternative too. Okay. I'll put up in a minute. I sent it out today. There's two tutorial documents that are K-map, and there's a second K-map tutorial as well. And those are pretty handy. Those actually help out quite a bit. It helps give some examples for students as well. Extension to 4 variables. This is another thing I say, okay, the first thing that you can see is that the first 2 rows are exactly your 3 variable map. That doesn't change, and then it flips the other way. And I say, okay, and they're like, oh, this is complicated. I'm like, well, this is the deal. I've got 4 variables. If you look at something like M15, okay, it has 4 adjacent squares. Each one of those differs by 1 literal, and there's 4 variables, so you have 4 nearest neighbors. You have 3 of them in 3 variable. So, this all works out the exact same way. A is your most significant bit, therefore it's 1 at the highest numbers, 8 through 15. D is your least significant bit, so it's going to be 1 for the odd numbers, 0 for even numbers, things like this. So I tell them this is where I don't want you to get, the map positions memorized by the letter that's used. I want you to understand that it's the most significant bit and then down to the least significant bit. So I tell them, we work through this, and they have to derive this chart and understand exactly why it's built this way. Then I said, but so you have the exact same situation here. So once you start circling ones, it all works out to be exactly the same. Here's 4. That's great. Okay, so I can circle 4 here. Now, this is 4 variables. If I circle 4 of them, it takes it down by 2. Okay, so if I can only circle 1 for a 4 variable map, I say, so now we're a little different. We have 4 variables. If I circle 2 of them, I remove 1, so I'm down to 3. If I circle 4, I'm down to 2, and if I can circle 8, then I'm finally down to 1, because this is 4 variables. I said, and again, you also got to keep in mind the 4. Now this is the sides wrap around, but now the top and the bottom do as well. So now you've got some sort of MC Escher-esque weird construct for how these things are all connected. But keep in mind the top and the bottom and the sides are connected. So one of the things that students see here's a simple 2, and then finally all 4 corners are connected as well. And I tell them, this, don't be surprised by this. It comes up a lot. This is B prime, D prime, and it comes out an awful lot. So then you read this exactly the same way. So basically you look at these 4, and you're like, okay, well that's C prime, D prime. That's perfectly fine. Those 2 in the middle, it's going to be A prime, B, C prime, and then the others are B prime, D prime. So then that's your overall function. And that works out fine. So, building up their skills on the 3 variable map and then going to the 4 variable map seems to work just fine. I don't see. I would say in general, students do well with K-maps. Once we work through it pretty slowly and build it up. I don't like to throw it all at them. And once they really understand why it's built in the way that it is, that helps out quite a bit. The final topic here are these don't care states. Okay, so I try to explain what this is all about. I say that many times, when you have some sort of a 4 variable inputs, you may have a situation that doesn't exist in the real world. There may be a situation where, if you have 4 bits, 2 of them can never be 1 at the same time because there's some sort of complementary function going on. So you'll have certain input combinations that don't physically make sense, for whatever that is. I've got one here. So I basically just took a function here and I said, okay, I'm going to put a bunch of, the don't care states are marked as X's. Okay, this example here is a specific type of don't care state. It has to do with BCD numbers. Okay, so basically if you're doing things BCD, it only goes 0 through 9 and everything above it is don't care. So I tell them that don't care is literally what it says. You put it on the map and you don't care if that X is a 0 or a 1. Okay, so I tell them that basically that the don't care states are always there to help you for the most part. They're just, you can treat them as ones and circle them, or you can ignore them. You do have to circle all the ones to make sure that your function is done correctly, but you don't have to circle all the X's. Okay, but use them if they help you. So for instance, we're going to start circling the functions here. We have these 4, that's perfectly fine. And then I've got this 1 down here by himself. There's a couple of ways you could do it. You could group it in a long column by the 4, or these other 4 here, which I chose. You can do it like this. Now that leaves off these X's that are at 12, 14, and 10. We don't need those. So we don't have to ensure that we circle them. Students will go through and do that. And that just, if you do it, what you're going to end up doing if you do that is something that needs to be further Boolean reduced, which is you're trying to avoid doing in the first place. So that's the full way. So this is always a good thing when you have don't care states. And we'll talk a little bit when we get into counters towards the very end of the material we're going to start discussing. And that is sometimes if you're designing a counter system, which is kind of like a pseudo-random counter where it's going in some sort of prescribed sequence, which is kind of random 0, 1, 6, 5, 3, 2, back to 0. Maybe you have a state that doesn't exist. It never goes to. If you include it, you can find out, from a design engineering standpoint, that if the thing were to get locked into that state somehow, what would it do? And so we actually do talk about going in and looking how you circle things as to because if I circle these X's, I'm assuming they're 1s. I'm assigning them to be 1s. If I didn't, I'm assigning them to be 0s. So it's something that comes out later when we do counters, because all things that that are to be engineered, they have to have some sort of backup system that says if it gets in a state that's not allowed, what does it do? Well, it has to pop out and go back in. So it can't just get into an infinite loop and just lock down. So anyway, okay, and then there's the answer for that. Final comments here about K-maps. Really, the students do need to show proficiency in all 3 areas, filling out the maps correctly from the truth table, grouping the cells optimally, and reading the map. The way I personally grade work that's done in this, which takes a lot of time, is I grade each one of these as different skill sets. So if I have a student that's got a circuit and then if they don't fill out the truth table correctly from the circuit, okay, this point's deducted for doing that. But then the thing is, do they take what's in the truth table and put it in the cells correctly? That's a different skill. If they do that correctly, that's fine. And then maybe if they don't read the map correctly, they lose some points for that. So it's not like at the end the answer is that the whole problem is wrong if they just missed some of those points. Because they may be very good at reading the maps, but for some reason they're having some problems filling out the truth table or converting that to they're making some mistakes there. And I try to address those and identify those problems. Again, I emphasize this probably way too much, but students do need to understand why it works and not just throwing it together. I want them to, once I feel that they really know, how this is laid out, then they do a better job of doing the reduction because they really can see it. And then like I said before, we have these lab exercises which really support this. We may do it on multi-sim or have them wired up, physically. That a complicated circuit, they do the reduction, and then they do this simplified circuit. And that is very motivating. they really do respond to that extremely well. I think this is, okay, so this is to the last part of the rubric. So that is, what we have is Morgan's theorem and logic simplification. So here, basically, can they do De Morgan's rules and apply them for doing Boolean reduction? They simplify these Boolean reductions. Can they know how to bring the ones into a K-map? Right here is I got to figure out my pointer, but how to group the zeros in POS K-maps. I'll talk about that. I'll call up another file for that in a minute. But the idea, so all of these I think the applied skills in the leftmost column easily can be done. K-maps, this just works very well. Even when they have struggle with Boolean algebra, we do go through, we do K-maps, they can get things done. This was something I showed before, but this is what I like to call the big picture, and that basically is one thing about this course is, of course, it builds up iteratively. It's almost a hierarchical process. Where you demonstrate proficiency in building circuits from a schematic, and you derive the functions, from the schematics or from truth tables or from the circuits. Then you reduce the circuits either by Boolean reduction or K-maps. Then you are ready to go to work on implementation, okay, which is I give you a problem, and now you give me a circuit that does that. Okay, so like I said, you have the problem specified, you develop the truth table, determine the function, reduce it, build the circuit, test it, and then I threw this in from last time, which is verify that once it's tested that you're getting the truth table that you actually have. So this is, so what we do in the labs here and in other places I've been is you build those key fundamental aspects of things of going through all these steps, and then you give them a few labs on implementation. I'll show you a few of the labs we use where they have to use all these skills and bring it together. All right, so any questions or comments at this point? I think we see a lot of the same. I think we see a lot of the things that similar things with the students. So all that seems reasonable, Ted?
Yeah. I think we see a lot of things. I emphasize K-maps from intro rest of the year. By all the labs that they do and stuff like that, they have to turn in project portfolios, and part of that portfolio is their hand-drawn K-maps. Right.
And your students are typically seniors?
For digital electronics, I get a lot of juniors and some seniors.
Okay, all right.
They're in their third year in the sequence of engineering courses that they take.
Oh, okay. So they've had some pre-engineering courses before they get to this.
Yeah, they get an intro to engineering design, which is primarily a CAD-driven course. We teach them Autodesk Inventor and the design process, and then they get a principles, which is a little bit of DC circuits and a lot of mechanical engineering and some materials. Okay. And then they can take either digital electronics or aerospace.
Right. Well, that's good because that at least they're thinking in the right way before they hit this.
Yeah.
Okay. Excellent. Okay. All right. So what I want to do here is let's see. I gotta get back to my pull up something else here. That's that. Where's okay. Tutorial. Not this one. Where's this? Okay, this is what I'm looking at. Okay, so this is the file that we had yesterday, and this is where I want to show you a couple of things that I think are pretty important. We talked about a few of these, and we talked about a little bit about some of the labs we were doing yesterday that basically going through getting the basic gates and all these types of things. So once we start moving on towards having them understand, simplification and these type of things, then we start moving on, moving into, how do we go through and support, these building up these concepts. So a lot of problems like this, basically here you've got a fairly more complex circuit here with some intermediate states. I then write them out, and then basically using truth tables. These are separate things, but one of the things is prove these Boolean expressions. So like for instance, these are like more or less this is A is a De Morgan equivalent, and this is the second most important law, and this is that thing that I constantly see students doing. I'm trying to nip it in the bud, so to speak. So I'm trying to prove that this is not the case. These guys actually are indeed true. So basically, they can take De Morgan's law for granted, but I want them to actually show. Just put it on truth tables and just knock it out. And you can actually see that that's true. So here's some more advanced lab, a little bit more complicated. They wire this up, and this is, like I was saying last time, and one of the real focus in this class is about troubleshooting. And so inevitably, I will give them the circuit, and I probably have half the class that will just build the entire thing. They'll just wire up the entire thing, and then they'll plug into the LED, and they'll say, hey, it doesn't work. And my response to that is, well, that's just too bad. What are you going to do about it? And so I say, okay, well, you don't, you would, if you were building a car engine, you wouldn't do it that way. You wouldn't just, put the entire thing together and just turn the key and hope. You would build it piece by piece. You'd be testing each piece, make sure it works before you go and include it in something more complicated. So I tell them, okay, well, you've got these little intermediate states. Once you wire this thing up, test this, make sure it's working right. Test this one, test this one, test this one. Then, if you know all those guys are giving you exactly what you expect, then if something's not working right, it's probably got something to do with this little OR network that you have, and then you can troubleshoot where it is. So these are kind of the real key things that it's a little bit difference between teaching EETs versus EEs. To be honest, we have such a strong focus on getting them to figure out what's going on. And of course, this is write-ups, and I do like to say, like, how many ICs do you need for this kind of thing? Can you change it? Can you make some, try to get them a little bit thinking a little bit how they can then change things. Problems in De Morgan simplification. Here's just a classic Boolean reduction problem. Basically, in a number of different ways. Okay, there is a theorem. It pops out in books called the consensus theorem. Okay, it's a very, very difficult theorem to implement. I know that some instructors have been able to use this as one of the rules for Boolean reduction, but the problem is it's usually very hidden and hard to find. So I don't like to use it, but I do have them prove it in any manner. They can either just go through and do it with Boolean algebra, or I have them put it on truth tables, do something to prove that. Okay. Now here's basically a lab that we do, which is Boolean reduction. So I give them 3 circuits. I give them this circuit, which doesn't reduce at all. Okay, then I give them this circuit here, which they have to go. So they have to wire this entire thing up, and then they have to take the circuit. They have to generate a truth table. They wire the entire thing up and show me that it works. Then they have to go through and they have to Boolean reduce this function, wire it up, and show me that they get the exact same thing. This is circuit 3, but this last one here is a lot of wiring. It's a very complicated thing, and it reduces down to, I think this one reduces down to A or C, and this one's like A, B, or C, something like this. So, and then they look at it and they're like, oh, well, it's just this. Okay, fine. But this is where I said this is actually really, really motivating. I tell them you can only use the 7404s, 8s, and 32s. So those are all 2-input gates, so they can't use 3-input gates, and they got to kind of think about it. So this is a nice exercise. It can take a while. It can take more than our labs are only 2 hours, and sometimes students can't get all this done in that time, especially trying to wire this entire thing up. So that's the case. Now, what I'll also so then they have to go through, do the schematics, I have to verify everything, and then they have to write up basically what I want them to do is to go through and say, okay, what's the motivating aspects of this? If you actually go to the internet, find the price of the chips, compare the cost of doing this Boolean reduction, and then think about you're making thousands of these circuits and how much money you basically saved your company by choosing this Boolean reduced form. That's pretty motivating. Okay, so here's an implementation project. So like I said, when we get to the last part of the slides, where it's like, okay, here's the full full deal. Okay, so now I basically give them some problems that are more complicated. Okay, so here's a problem here that basically basically you take this as a 4-bit number here, A, B, C, D, pushes a 3-bit output, where x2 here is 1 if the base 10 number is divisible by 3, x1 if the number is divisible by 4, and this one's divisible by 5. If it's not divisible by 3, 4, 5, it's considered to be a don't care. Okay. So these are 3 different functions, and this is something else I try to emphasize. You can have 4 inputs, but you have 3 different functions pulling off of those. There was a plot I used a couple times last lecture, and so basically I say, okay, so they go through, and from this implementation, which is usually the case, you directly write out your truth table given what it is you're trying to do. So they can definitely write out the truth table. Then I said, okay, now here you've got 3 functions. Do them all with K-maps. Okay, and so they reduce it with K-maps. I say, okay, do x2 and x1 using only NAND gates, and do this one with only NORs. And then we'll talk about next time. On Tuesday I'll talk about multiplexers and decoders and things like this. And sometimes I have them do that. Same thing. Here's a couple more problems. These actually turn out they're fairly hard to design. By the way, if you actually go through and try to design implementation problems, what you end up getting that I have found is you find some terrible K-maps and circuits that just don't reduce, and you have to be fairly clever in working this out. So if you want to use these, have at them. I didn't include the solutions, but if you want to, I can try to send them to you. I'd have to find them. Same thing here. So this one's a little bit more mathematical. It's a little more complicated. And here the same thing. It's like you want to build a circuit that takes a 4 input from 0 through 12 and lights an LED if the input is by 3, 4, or if it's a prime number. And then basically you're taking 0 through 12, so you're taking 13, 14, 15 as being don't care. Put those in that. So you're doing a couple of these kind of implementation problems. Lab 5 is the first one where since we've got all of our basically all of our techniques down. So basically we've got the ability to build circuits. They're now using all kinds of nice bus wires. I'm trying now to get them to make the circuits look a little bit neater, and they've got some rudimentary troubleshooting skills on this. I say, okay, well, here's a problem. So here's the first implementation lab that you have. And so basically you've got this. Basically got these inputs. Okay, so you've got WSAG, and I say, okay, these are like sensors, and go back to the example I gave of if you have your key in ignition and you open the door and the alarm goes off, it's the same kind of thing. That's an AND gate between those 2 sensors. So here you have a situation that this jet company is going to put some circuitry that's going to sound off some alarms given some particular situations. You have basically a sensor on the wheels. You have an airspeed sensor, you've got an altitude sensor, and then you've got a sensor saying whether or not your landing gear is down. So you're given 6 different conditions, okay, for this light to go on. So there's six different conditions. Some of them are very simple. Some of them are slightly more complicated. So the students have to go through, and they have to look at each of those 6. And they have to write those out in Boolean expressions. They put them on a truth table. And then I try and then basically get them to do some reduction. I think this was actually done. They Boolean reduced this before they had K-maps. Okay. And then once you get simplified this circuit, then they wire this up and they see if they get this to work. Then so what I also have them do is, in addition to building it, I have them simulate it on multisim, and that's where I also have them figure out the reduced circuit. They can do the Boolean reduction on multisim, and then put it in NAND gates, and they can see how that works from a software standpoint. And that works really well. And then I ask them some questions about, is there any advantage to building without NOR gates? Does this function, would it be implemented easier if it were NOR gates? Is there any way you would improve the circuit by the ways which you really stated? And there's some ways to save chips if you use XORs or something like this. There's some ways to do that. But basically what I'm saying is, right now, is there a way to make this better if you change some of the inputs? Like right now it says the input line S goes high if the airspeed's above a flight speed. Well, what happens if you reverse that? If S goes high, if it's below the flight speed, does that maybe gives you K-maps which reduce even further? Okay, so that's kind of a design standpoint to things. You know, maybe if you have those sensors are flipped in some way, if they're doing the opposite situation, you might make for a simpler circuit if you orient those sensors differently. And that's a design thing, and it's something that students think about, at least on this exercise. And that's a pretty good one. We also have one that the students are doing. I didn't include it here, but it's the lab after this one, which I'm currently running right now, which is it's an alarm system inside the house. You know, so this is basically you have a sensor on the windows, and you have a timer if it's after a certain time at night, and then you have something on the window, sensors there, and a couple other sensors around, and so they also get the concept now of what a latch does, and so they have to, even though we're not getting into latches yet, you know, I have them build one to say, okay, well, if you think about the concept of an alarm system, you know, if you open the window and you close it, you know, you don't want the alarm to go off when the window closes because that's not good. You want it to hold, and so they build this latch to hold the signal until it resets it, and that works really well. And that they once they kind of get that design, so all these implementation labs I think are very beneficial because you really get the full experience of designing. You know, here's your problem, solve it, and build me a circuit that does it. That's a very gratifying thing for the students to see. So that works extremely well. And just a couple more comments. I wanted to pull up one of the other things here. Wait, hold on a second. I want to show. Okay, so here's the K-map tutorial that I sent out. So basically, it's very similar to, but in more detail about the stuff I put on the slides. So basically, talking about how the minterms are organized, you know, knowing the maps, talking about how adjacency, and then how you start reading the maps in the way that I kind of describe them, where it is, you know, and then basically going through all those processes about, okay, here's how it's organized, here's how you fill out the map, here's how you read the map, okay, and then trying to emphasize again that do the proper groupings. But this is a pretty good, this is a very helpful document. You know, students do like to have this. I think anytime you can spend, once you really identify problems that students have, if you can write a tutorial document that specifically addresses those issues, it's a lot of work to do it because you're basically writing almost like a little chapter of a book or something. But of course, you only really need to do it once. So that's the good aspect of it. But I find these things to be very helpful, and I put them up there, and the students really like to have them. And it's, because it's difficult for them to be listening to what I'm saying in class and taking notes and being sure they got everything and processing everything. So this does help out. And of course, I go here to the four variable map here, just like I did before. This is, which one is this? Okay, so this is one of the combinational logic tutorials here. This is the one that goes. There's a bunch of stuff in binary numbers, but then we go into De Morgan's law here and talk a little bit about that and how to do that. That's kind of locked in that document, which you also have. And then the second K-map tutorial here is where I start talking about now implementing don't care states, what it means to have the don't care states. You don't have to include them, and if they're beneficial and this kind of stuff, and with a bunch of other examples on how to read them. I do talk here about using the product sums logic. That basically sometimes you may have a situation to where the function has fewer zeros than ones. And so basically, trying to emphasize, if you're doing this, you've got to keep in mind that it's in this form, A or B or C, and also you start circling zeros in doing this. Not only are you circling zeros, but now all of your columns are inverted. Okay, so this makes it's a tough one. Students they just get the feel, they understand K-maps. They're like, okay, let's just screw everything up and really mess with them a little bit. So usually I don't do this a lot, but I will give them an exercise. Say, circle all the zeros using the POS logic, write that expression out, go through, do all the SOP logic with all the ones, and show that those things are equal. Because I want them to understand that there's different ways of doing things, just like I was talking about with the sensors. If I could orient the sensors and reduce my circuit, maybe it's easier to aim towards the zeros instead of the ones. It's just another way of thinking about things. So that is sometimes helpful as well. There are lots of problems that I have here. I think this is the same thing we're just doing. So that's looking like the bulk of what I really want to talk about today. The next topic we're going to start talking about decoders and encoders, multiplexers, demultiplexers, adders, things like this. Start going into the next level of combinational logic, which is in hierarchical fashion.
Basically, give them a better idea of what they could.
I'm sorry, I didn't catch that. Can you say it again? It was real bubbly. Now I'm not hearing anything.
That they want to take.
What's that?
Can you hear me?
I can hear you now.
Okay, I'm sorry. I had to switch devices because my batteries were running low. Sorry about that. I'm just listening in, so.
Okay.
Thanks, Ralph.
I couldn't hear the other caller that had the question though.
Sorry about that.
Okay. Well, pipe in. We have another question. So, because right now this is basically all that I really wanted to talk about right now. So definitely, if the questions, just let me know. This is probably. Let me just. Here we are. Okay, so there's nothing really left here on the screen. Back here. Okay, so for now, I'm interested. Definitely want to hear your comments about experiences that you have had with some of this. What you found that works, what you found that possibly doesn't work. So, any comments, anybody?
I find with most of my students, when you hit the K-maps, we teach a vertical method rather than your horizontal method.
Sure.
And I try to emphasize that the reason that the groupings is there is so that when you do get a pair or a set of four or the groupings that we teach, that it eliminates one of the variables. So we'll put the variables on the sides of the K-map,
right,
so that they can see that there's an A and a not A in one groupings and or a C and a not C in another grouping, and then eliminate their variables that way.
Right. So it sounds like kind of like a hybrid between these two.
Yeah. I also try to emphasize that the reason why there's the blocks that are there is because they're representing specific input lines.
Exactly.
And when I first teach it, I'll actually just at first have them put the inputs in each block and then put in their ones and zeros so they can see how the truth table is actually implanted into the K-map. Mm-hmm. And it just gives them a little bit of insight. But I like your pointing out of the how there's only one changing variable at a time. And so we'll throw that at them to look at a little bit more patterns there.
Yeah, but I think it's actually good that you're actually trying to, anytime that you can basically kind of keep reminding them that the variables are actual wires. I think that's a very handy thing because it's just, it's very easy to get lost in the math. And, when you look at it, you're like, okay, this really is actually a physical thing, and that works out very well. Yeah, absolutely. Do you deal with, talking to students, do you deal with the POS forms at all?
I pointed out to them, but we mostly do the sum of products simply because it makes, when we get into doing universal gates, it makes the reduction a lot easier.
Sure.
So we don't stick to, I pointed out to them, I show it to them a little bit, but we don't do any major projects in it or anything like that.
Yeah, we don't actually do anything in the lab that way either. It really is just more of an academic exercise.
Mm-hmm.
Right, absolutely. I agree with that. Now, how many labs do you do with your students?
Oh, shoot, we're like almost constantly doing something.
Okay.
But our labs are more project-based, and I'm trying to visualize how you do your labs, because like the one activity that you had here where you gave them the 3 circuits,
Right.
and you said that was like a 2-hour lab.
Right.
There is no way I could get my students to wire that in 2 hours.
Well, neither can I usually. Yeah, it's a tough one.
Yeah, so I was looking at that. I might add that activity in, but I'd have to make it more of a multi-sim exercise than anything else.
Yeah, actually, when I was at OU, we had a bunch of very complicated labs, and we found that some of the labs were so tedious to wire that the students were not actually getting much out of them. They were just becoming work, just to try to wire these things up. And so, so what we did is we would have certain labs. We wanted to be sure that we nailed down certain concepts. And you'd say, okay, take this thing and put it on multisim and do it on multisim, just because it's just going to be simpler to do and quicker. Rather than saying wire this entire thing up and you're just constantly going to be chasing down bad connections and bad chips or gates or something. It's just going to be very frustrating. So there was a point where we kind of, I don't want to use the word bail, but I mean to some extent that is it. There was a time we said, this is going to be much better if we just simulate it, because we just don't have all day, But yeah, that's quite true. I don't have a real problem with that. I think that I've had lots of times where I've had, I tell students, okay, you really need to get the lab in. If your wiring's not working, you still need to show it to me on multisim, and we'll try to work this out later. But yeah, that's quite true. Yeah, that's why I extended the lab of this class from 2 to 3 hours. It's going to be 3 hours starting next fall, because it's just not enough time. And as you know, I'm sure that you see with your students, some students pick this stuff up very quickly. They just, it's like they sit down at the wires, they put them in, it makes perfect sense. And some people are just afraid to do anything. So some people can really just, even simple circuits can take a long time.
Yeah. And, except for the Boolean Algebra, most of my students don't have too much of a problem with this part of the course.
Right.
Until we start hitting sequential logic with flip-flops and state machines and things like that.
Right.
And then they all go a little nuts.
Yeah, it definitely, the course takes a huge turn there. And there's a couple of exercises I think are very important, and I'll be bringing this up. I'm going to start talking about that kind of stuff next time. We'll finish up the combinational logic with multiplexers and decoders and stuff like this. And I've got a couple like exercises that I haven't seen in books using multiplexers, which I think is pretty interesting. Kind of gives them a real feel for novel ways to use multiplexers. But yeah, it's absolutely that's the case. Almost every class I teach, once you go to sequential logic and you start bringing in clocks and timing diagrams and asynchronous signals versus synchronous signals and state machines and counters and registers, it's a lot, no doubt about it. Yeah, I mean this class when Cincy State was on terms, there was one term was combinational logic, one term was sequential logic. It was split out over 2 terms, and I guess that's not the worst way to do it. It can be quite a lot. So anybody else have comments? Okay. Then, I mean, as far as I'm concerned, this is where we wrap up today.